Good morning, everyone.
Good morning.
I'm Jasmine Jacobs, and I will be presiding over today's lecture. Today we have Dr. John L. Hall, Nobel Laureate, and he will be speaking to us about the proposed space experiment to test Einstein's assumptions about space, time, and the speed of light. On behalf of the STEM Academy and the UAPB student body, we would like to welcome Dr. John L. Hall and his wife, Lindsay Hall. The program will proceed as follows.
Good morning. This is a very special day here at the University of Arkansas at Pine Bluff. Thank you so much for presiding, Ms. Jacobs. She has an important title here. She is the president for the STEM Academy. The STEM Academy is a special enrichment program in science, technology, engineering, and mathematics here at the University of Arkansas at Pine Bluff. In addition to learning about STEM areas, our students also learn about leadership. So they have their own club, their own activities, they do community service, they maintain Prexy Drive, which is a major thoroughfare here on this campus. And each week they have a program. Sometimes it's for information about a conference, but many times it's a guest lecturer coming in, giving information on a particular research topic, but also providing an opportunity for students to learn about their programs for summer internships and also for the possibility of graduate school. But today is a very special day, and I would like to extend thanks to the UAPB family for coming out to take part in this special occasion. It's not every day that you get to come face to face with a Nobel laureate, a world-renowned scientist, not just a state, not just a regional, not just the United States, but a globally recognized scientist. So students, I want you to write it down. If you have a diary, I want you to write down that this was the day that you not only heard, but had an opportunity to shake hands with a Nobel laureate. For an event of this magnitude to take place on this campus requires the work and dedication of a large number of people. First of all, we would like to extend thanks to the National Science Foundation for the funding provided to this campus, and to the American Institute of Physics, which actually coordinates the Nobel laureates. And there is a Vice President Emeritus, Dr. James Stith, who actually introduced us to this association and was helpful to us in making the arrangements to get Dr. Hall and his wife to campus. But to get to Dr. Stith, there was a person from Arkansas who was very helpful to the STEM Academy, and I want him to stand up. Mr. Al Ashley, would you please stand up? This is the gentleman that I want you to recognize and applaud. For we were at a meeting of the National Science Foundation, and Mr. Ashley told me at lunch, he said, I want you to meet Dr. Stith, because he is the person that can get a Nobel laureate to your campus. And I tell you, that was one of the best lunches that we had. Not the menu, but the opportunity to make contact finally with Dr. Hall. So what I would ask you to do today, students in particular, and we have several faculty members here, thank you so much for being here. But students, I want you to listen, and I want you to ask questions. This is your opportunity to ask an expert whatever it is that you might like to know about the topic that will be presented. Dr. and Mrs. Hall, welcome to UAPB. Welcome to Pine Bluff, Arkansas. Welcome to Arkansas. students. When they leave here, they will be going to Fayetteville. But what I want you to know is UAPB extended the invitation, and you get to hear them first. So thank you so much for being here, and now we are going to yield the rest of our time to our primary reason for being here, and that is to hear you, Dr. Hall. Thank you.
Dr. John L. Hall was raised in Colorado and earned his PhD in 1961 at Carnegie Tech in Pittsburgh, Pennsylvania. Hall pioneered the use of stabilized lasers to accomplish measurements of unprecedented accuracy and intrinsic physical interest. He introduced the methane helium neon stabilized laser, and with his NBS team, used it to measure accurately the speed of light. In collaboration with other national metrology institutes, the SI meter was redefined in 1983. His group has stabilized various tunable lasers, even diode lasers, to sub-HD line widths. He showed how fiber noise could be actively suppressed to deliver phase-stable light at a distant site. His group pioneered the optical comb techniques, which allow simple and direct measurement of optical frequencies. For these works, he was awarded the 2005 Nobel Prize in Physics, jointly with two of his colleagues. He has received numerous other peer-generated awards, has more than 235 refereed publications, and holds 11 U.S. patents. He has been thesis sponsor for 15 PhD students, co-advisor for 50 more, and his laboratory has hosted more than 150 postdoctoral professional and visiting faculty colleagues from all over the world. Please join me in welcoming Dr. John L. Hall.
It's a huge pleasure for me to be here today. The business that my wife and I have been in for now 85 years combined is interacting with young people. She did 7th grade, trying to bring the knowledge of English to young people at that age. You can understand might be challenging. And I had an easier job. I was in the University of Colorado, where I have enjoyed meeting young people with great enthusiasms and trying to expose them to the fun of physics. So I'm really glad to have the chance to come here. I'm going to try an experiment today because I think you maybe even in a little bit younger age than me probably have the feeling that the last year or maybe 2 years are been completely exceptional in what kind of amazing things have happened. And we have unprecedented storms in Haiti. We have unprecedented earthquakes in Japan. It's just every crazy thing is happening. And so that means that it would be good for us to look a little broader than just the talk that I had originally proposed to give. So I think the topic that is the most powerful and the most human is about tools. That's how we're separated from the rest of the people. Errors can occur, and the errors are not so critical. We need to understand when they happen and try to go around that, and we are completely comfortable using trains now, even though it was embarrassing in 1895 for somebody. How do you figure out what you want to do? Here's a young guy who was pretty good. He was in the University of Western Australia in Perth. And the classes were good. They taught him about Maxwell's equation, about electricity, and especially, as you see, he learned something about shielding. Gauss's law teaches about that, and he is hiding inside the metal shed, and you notice no sparks are going to him. Now, if you think about what would your mother say if you had that set up, it'd be the same as mine. Dude, what are you doing that for? This is completely a waste of time, it's dangerous, and so on and so on. You know that story. Well, what did he said it's good for? Peter Tarrant says, oh, this is serious car protection. The claim is that this can even protect your car if you would park it in Rome, and that's a pretty serious rating. So that's one kind of picture. of how to have fun, and issue is, where does that lead? So you need to follow somebody that maybe has a good highway. This gentleman at a young age had a highway, but in an older time, he wrote a guide, Young Beginner's Guide Winning the Nobel Prize. Well, okay, that's not completely the way that you want to go at it. You should really be doing something that's fun. And then more than that, there's no guarantee and no refund on if you buy his book. So that's a bit of a problem. Other visions of what is important in life, this is available in the next university to us. It's up the street 30 miles. And you see that if you buy anything from them, even one of the portable safes that you can carry all your world valuable things, put them in the safe and then just carry it around. Now that doesn't sound exactly right to me. But anyway, you buy a Glock or some ammo or something here and you get a free Nobel Prize. So I thought, I've never seen a sign like that. So the thing which we all share and you young people will see happen is this accumulating speed of computing. That's to say, having mechanic stuff that does what we do ourselves. So you know that a few years ago, the IBM put up a machine that beat the world chess champion Garry Kasparov on one game. It did 200 million evaluations of chess position in a second. And a year later, they had increased the scale of that, not from 200 million to 111,400 million operations per second. Gigaflops, floating point operations. And that won the match. So that's starting to say, in a simple game like chess, where there's a definition of how you can move the pieces, okay, then you could believe that it would be possible to program that. But just a couple of months ago, the most incredible thing, excuse me, I'm out of order. You can get yourself a chess program that plays better than anyone in here, I guess, me absolutely included. It's free of charge on the internet. Runs on your home PC. So you can have teraflop machines. The Cray company have made more and more. Now the cheap way of doing it is to simply buy a lot of PCs, PC clusters. How about 62,000? That almost seems an absurd way of doing it, but it works. And that is one of the most powerful computers that we have now that is available for doing non-classified work. Home computer power passed up humans when the first program came out for Apple computer. It was called VisiCalc, and now the Microsoft people sell this as Excel, which I'm sure that most of the people here using. Now, the thing which was impressive is this thing that happened a month ago, that this computer that was called Watson playing Jeopardy. Now, Watson, as a computer, has to listen to human speech, figure out what that is, what's the question, what is the context of this, look through all the memory, and come back with that and beat these two human guys, Rutter and Jennings. And this program managed to do that 3 days in a row. And that is an absolute turning point in having sort of general purpose. I don't know what the problem is going to be, but I'm kind of a lumbering smart computer and I can do almost anything. Tell me what you would like. I want to play Jeopardy, and he wins. You can see that just a little bit from now, human and computers are going to have the same horsepower, and I almost can guarantee you that 10, 15 years from now, computers are going to use us as the agents for bringing a tea for them in the afternoon or whatever they would like to have. It's really interesting to think about this. This is a turning point in the whole history of the civilization on the earth, that there will be something which we have made that outdoes us. So let me spin through the topics that I think might be fun to talk about. I'm an old geezer, and so I have grown up in a time when different things were important. So for us, the absolute correctness and the elegance were valued things. And it's reasonable to think that something that's really important would take a long time. The work was done by an individual typically, and it was really important for you to be lucky. Let me say that again. It is really important for you to be lucky, and luck comes if you're prepared. So you're picking a good field and trying to understand what the deal is, what's the insight. Then you can make up the rest of the little details and things as you go along. That way you're going to have 25 years of guaranteed employment, and maybe 15 years you'll have to be a supervisor for the next generation of people that come in. And now 20, 30, 40, 50 years have gone by, and let me say how I think it is now. That the modern system rewards the first as opposed to the best. Real progress depends on a broad knowledge, and so that's going to mean you're working as a team. If you know just a little bit of something that's outside your domain, that may be absolutely essential in saving, because the problems we deal with are so broad. So the social skills actually might be essential for your work, because you're going to be working in a team, if you are in research or in any kind of non-manual kind of effort. So again, I'll say that insight and creativity are the key values, and if you need details, just a little bit of practice, and Google will tell you what all that was. And the final remark for you, as if I was your parent or cousin or something, is that it really is important for you to know what you like and what you're good at. And the best thing Winston Churchill said was, if you find what is your special thing and you like to do it, you won't have to work another day in your life, because you go to the office and it's not work, it's fun. Man, I would pay to be able to do this kind of stuff. So there's a beautiful book you can read in an evening by Ken Robinson called The Element. He's exploring this idea, which most adults have already come to understand. Now, you don't always have people recognize your work as important immediately. So there's a guy who made nuclear magnetic resonance, and he did that paper in 1948. And that's, he has 4,000 citations to that. So I say thanks to Nicholas Bloomberg. Without his ideas, I'd still be in graduate school looking for my signal. At that time, we had a little kid. He ate $1 jars of applesauce every day, and there was no way I was going to be able to pay for that. So there was a critical sentence in the appendix of his paper. So in detail, I like one particular way of doing it. So this is my presentation for the 90th birthday for Nico Bloomberg, and that was held last year. He made his contribution in 1947, and now many of you will have been to the hospital and had magnetic resonance images made of you. And that's a really practical thing that nobody had a dream about, and it came out of this. So it's science that's done for curiosity, and then goes into a journal. It's safe there, and somebody sees that and they try to study it. Some students add to that. I added to that in my time, and then later time it turns out it's seriously useful. So we've had a beautiful time living in Colorado, Lindy and our 3 kids. There's glorious mountains. If you like skiing, this is a wonderful place. We've had maybe 1,000 dinner guests. I don't know what the number is, but it's sure been a lot. And here is the team that was part of my group in the year 2000. I pick on the year 2000 because that is a place where something quite amazing in physics happened. That was this guy got picked out, as you see, and entered into a new task. So I'd like to say just a couple of technical things which I think should be clear enough about how do you get 1 million lasers that are all stabilized. And its work is done in this place, which is called Gila on the University of Colorado campus. Here's again these nice mountains. The length of time of this has been so long that it's now time for a new colleague to take over, Dr. Jun Yi. The people, your parents and grandparents have sponsored through the National Science Foundation, NASA, and the NIST. And one of the parts which Lindy and I have contributed to is the transformation of this building, which you see now in a later form. This is a 1964 kind of picture, and these people are now 50 years old and provide grandchildren for us. And what happened in here is a discussion about exactly what was described by Professor Benjamin earlier about interpersonal respect and learning from each other. So roughly speaking, we were 12 people out in a place where there could still be Indians around. We circled the wagons at night, so to say. We talked to each other. I didn't need to learn about vacuum because one of my friends did that. I was the electronics guy, somebody else did mechanics. And the result of that is we had a complete set of people and an enormous horsepower in this place. We've had 20-something professionals and 3 Nobel Prizes, and that doesn't compute. There's no way that could compute. So there's something about doing that. Well, let me tell my technical story then. In the beginning, there was the word from Arthur Shallow and Charles Towns about how to build lasers. And in California, at the Hughes lab, Ted Maiman built the first one with a ruby laser, and Ali Javon built the first one in gas lasers. The ruby laser ran as a pulse, and if you have a pulse laser, then it's going to be powerful, and so you'll probably be able to see something nonlinear happening. The lasers that Javon made ran continuously, and that makes them stable and ultra-sensitive, and that's the highway that I've followed. And so this 1960 epoch, this laser was announced 6 days after our first sun came, so I didn't actually know that this had happened for a little while. 1960 onward. So here is now 50 years later of lasers progressing. We have the pulse lasers, and they go, and I played a little with lasers that could burn razor blades or make sparks in the air. But it was clearly more interesting to play with lasers that would be super stable and can do things. So I'm going to give you a few little signposts going along this top highway of the stable laser highway. So that begins with having a laser that, if you tune it, it has some output power which is totally broad, and it has some kind of peaks which are super strong and narrow. And that is because of my synthesis of some ideas which were known by putting a gas, methane gas, inside the laser cavity. And then that's so sharp, then we could define the frequency, and where do you start with frequency? You have to start with a definition. So that's a cesium clock at 9 billion oscillations in a second. And where you want to end up is 1,000 trillion oscillations in 1 second. So that's a factor of 115,000. And how in the world could you ever make a measurement across that kind of a factor? So the first issue about this was, you know, it's like a government plan. It's clearly not the best way. You have to just multiply by 2 and 2 and 2 and 2, and you can finally get there. And so it's not a very efficient way of doing it. So here is one of the 3 laboratories and 2 of the 12 people that were involved in that experiment into the 70s and early 80s. These lasers are hugely long in order to get enough power that one can use this nonlinear interaction that I described by the factor, getting a factor 2 frequency measuring. So what that led to was finally the frequency measurement, and that led to changes. The meter, which for time had been a million waves of some krypton lamp, was replaced by a different definition. The speed of light is some exact number. And I don't think we'll have an exam now because you probably already all know this 299792458 meters per second exactly. So if you talk about meters or centimeters or miles, anything in length, it ultimately is connected not to some bar that's in length, but instead through the speed of light and to the optical definition. So that's kind of a demotion of the meter. And what's happening now, I went to meet with lab chiefs in London in January, is demotion of the kilogram. So now the kilogram is a piece of stuff that's kept in Paris, and it's going to be replaced by quantum mechanical relations. And it's absolutely fascinating to see this happen. Okay, so I made one laser, and my buddies at other labs made a whole bunch of other lasers, and how we're going to ever find out what their frequencies are. The idea was already talked about in 1977 and 78, but it kind of came in under the radar and nobody knew it because it was so counterintuitive. If you have something which is sharp in time, normally that means that it is diffuse in frequency. But if you have a bunch of pulses that are sharp in time, then that can be give a bunch of lines which are sharp in frequency. So time and frequency, or time and energy, are connected together. Another part of this story, which we've already been on, is that good ideas can come in every group and every country, and I guarantee that Americans are not anything special about that. Those pictures before that showed a Russian guy who was a major contributor in it. So now I'd like to then tell you a couple of words about an optical comb. It's something which you haven't probably heard about, nobody has had before, just got turned on in the year 2000. It's kind of like a crescent wrench or a screwdriver. If you never had heard about that, you'd think that's kind of weird. But that's because we've had those for 100 years. But optical combs we haven't heard, but you're going to use it. If you do anything technical, this will be part of your work in some way, I guess. So the issue is that the pulses are repeating, they're regularly spaced, they have some detailed shape which can be explained by little waves oscillating inside it. Maybe those waves are the same, maybe they're not the same. And that's connected to a repetition rate of some laser. So the latest news from this 1999 time was that there was a goofy idea, but we didn't have any components, so that was just a crazy dream. But we did finally get short pulses with a width which was a decimal point, then 14 zeros and a number. And we made something similarly. We made lasers that were so stable that they were 10 to the minus 14. And the breakthrough part in this was coming from a totally different group of people, about not just a factor of 2 nonlinearity, but a factor of 1,000,000. So what my contribution was is to merge these 4 separate technologies. So that was an idea from 1977. There was a paper by their group, Hensch's group, in 2000. Our paper was in 2000. It came out 14 days later. And by the end of 1 year, there was 20 papers from the world community. Everybody was ready to pounce on this because we've been struggling with those huge long lasers, and there's just no way of doing it. And so this world physics team got recognized that people in Sweden understood that this was really a breakthrough, and reached into the stack of papers and picked out a few names, and so I was one of the people that got selected. But this contribution has 20 people that could equally well be chosen. What's magic was this. This is a piece of optical fiber. It was intended to be a prototype for what we put under the ocean. The diameter of this is 100 microns. That's the same thing as I have just a few left on the top here of hairs. This is special fiber, though. It's not homogeneous. In fact, it's made in this special shape. And the way you make it is to take a rod of glass, and there's the rod, and then you take tubes of glass and you stack them up around it. And then when you're all done, it's about this scale. And you give it to your buddies that have the drawing tower for fibers. And in a couple days, they give you back 20 kilometers of this because they've stretched it out and they got thinner. And then they can put it on a spool. And that's what's under the street. And you see these guys with a truck, and they dig a trench and put down a big yellow pipe. And inside that's 50 or 100 of these fibers, but not this kind of fiber. They put them down and it's just all homogeneous. This fiber has a special place in here And the light is caught in there because the reflection is so strong where it can't get out of this place. And it's very small, so if you put strong light in it, it's very powerful. And so it can be nonlinear. So in this laser engineering conference, this guy showed a pulse of red light coming in, and it changed its color as it went along. And I saw that, and I knew that this is pulsing repeatedly. It's showing all these colors, and it's happening at 100 million times a second. And I almost died. I was so excited to see that. It's simply transforming kind of experience. In fact, it has turned out to be the dawn of a new epoch. So this serious nonlinearity is based on what's called microstructure fiber, and the speed of light in it is, the technical name is the dispersion is 0. It means that any color you put in has the same speed. So we put in this band of colors, and they interact in a nonlinear way, and they've broadened out. In the beginning, it's totally magic. You can get this spectrum that goes clear from red to blue. It covers factor 2 in the wavelength of frequency. And technically, it turns out that you can package it after you understand how to do it into a small little box. The fiber, little tiny piece is stretched in here, and these are microscope lenses that focus in and out. So that makes it possible to have this broad spectrum of light available. And if somebody's interested, I can explain the minor technical contribution that our group made about how to lock this system together by using its broad bandwidth.